Hello everyone, myself Professor M.J.Birajdar from Pharmaceutical Chemistry Department, ANS College of Pharmacy, Latur. Today in my lecture second, I am going to discuss about sympathomimetic agents. In my previous lecture, I have discussed about the nervous system and its various parts and detailed discussion about the autonomic nervous system. In this class, now I am going to discuss about the sympathomimetic agents. Then what are the sympathomimetic agents? How it is defined as? These are the chemical agents or drugs which mimics the action of sympathetic nervous system by reacting with the adrenergic receptors, called as sympathomimetic agents or sympathomimetic drugs or stimulants compound which mimic the effect of endogenous agonist of the sympathetic nervous system. Classification of the sympathomimetic agents. These are classified into three classes. Number one, direct acting, indirect acting, and mixed acting. Example of direct acting: norepinephrine, epinephrine, phenylephrine, dopamine, methyl-dopa, and salbutamol. Indirect acting examples: hydroxyamphetamine, pseudoephedrine, propylhexedrine. In mixed acting, sympathomimetic agents are ephedrine, metaraminol. Next one is a SAR of the sympathomimetic agents. It is a very important part of the sympathomimetic class. So, what is meant by SAR? SAR is nothing but the structure-activity relationship. Why it is important to study the SAR of the particular class of drug? SAR of a class or particular drug which shows particular biological activity of that drug by alteration of the or changes of a drug molecule by substituting or by replacing the functional groups, by enlarging the chain, side chain, little bit minor changes which may occur in the drug which affect on the biological activity of that compound. So it is called as structure activity relationship. So it is very important. SAR of the sympathomimetic, or it is also called as beta phenylethylamine class. So this is the catechol-nucleus which is very important for the sympathomimetic activity. So it consists of two carbon atoms, 1 and 2. It is designated as alpha carbon and beta carbon, and this is the amino nitrogen in the side chain which is present on the catechol-nucleus. So these are the two hydroxyl groups which are also important for the activity. This is beta carbon which is substituted by hydroxyl group. This alpha carbon, it is another substitution which may occur, maybe methyl group, or any other substitution which affect on the activity of the compound. Maximum activity is seen in the beta phenylethylamine derivatives containing hydroxyl group in meta and para position. This R1 group substitution on the nitrogen, this is the terminal nitrogen amino group which increases in the size of R1 substitution, which is increases the beta activity, which decreases the alpha activity, and the decrease the degradation by the monoamine oxidase inhibitor. If we have substituted the tertiary butyl group, it increases the beta 2 activity. Example, quilterol. It is a drug which forms by substituting the tertiary butyl group. Larger. Also it is shown by the alpha blocking activity. Labetalol is another drug. So This is the formation of the various catecholamines. This is the optical isomerism, alpha carbon, beta carbon. For catecholamines, the more potent enantiomers has the R configuration. This enantiomer is typically several hundred folds more potent than the enantiomer with the 1s configuration, means R configuration is more potent as compared to S configuration. R1 substitution on the amino nitrogen. These are the amino nitrogen. R1 substitution already I have discussed in previous slide. If R1 substitution on nitrogen increases in size, the activity of beta agonist increases. This determines alpha or beta receptor selectivity. Primary and secondary amines have good adrenergic activity, whereas tertiary amines and quaternary ammoniums do. If the size of the substitution increases on R1, it decreases the alpha activity. As the size of the nitrogen substituent increases, alpha receptor agonist activity generally decreases and beta receptor agonist activity increases, as well as it protects the amino group from the undergoing metabolism by monoamine oxidase inhibitor. These are the changes of the drugs by substitution on the nitrogen, terminal nitrogen atom. Hydrogen, the structure for leads norepinephrine, which shows the beta receptor agonist activity. This is the epinephrine. By replacement of hydrogen, methyl group is substituted. The structure form is epinephrine. Next one is a isopropyl, isopropirenol. It is short form is ISO, which is beta 1 and beta 2 agonist. Secondary structure is there, and tertiary butyl norepinephrine, colterol. This is the tertiary group, which is cyclic beta 2 agonist. R1 substitution on the amino nitrogen. Large lipophilic groups have an alpha 1 blocking activity. Example, labetalol. This is the structure of the labetalol. R2 substitution on the alpha carbon. This is the alpha carbon. R2 substitution. Small allyl groups, that is methyl, which are substituted on the alpha carbon atoms. If ethyl group is substituted, more beta selective activity shows the structure. Example, ethyl norepinephrine, which increases the CNS activity, and it also increases the oral activity and duration of action also. S configuration, S-methyl group, which increases the alpha 2 activity. R2 substitution on the alpha carbon atom. The substitution by small alkyl group slows metabolism by more, with little effect on the duration of action. Lipophilicity of R2 substituted compounds often exhibit enhanced oral effectiveness and greater CNS activity. An ethyl group in this position decreases alpha activity far more than beta activity, according compound with beta selectivity. Example of this is ethyl norepinephrine and isoethyrene. R2 substitution on the alpha carbon atom. Alpha methyl norepinephrine, it is the erythro isomer that possesses significant activity at alpha 2 receptor. This is the structure of alpha methyl norepinephrine. Fourth number is hydroxyl substitution on the beta carbon atom. This is the beta carbon atom. Hydroxyl group is substituted This hydroxyl group is essential for the activity, generally decreases CNS activity largely because it lowers lipid solubility. Compounds lacking the hydroxyl group, in example dopamine, have greatly reduced adrenergic receptor activity. Substitution on the aromatic ring. This is catechol nucleus. On the aromatic ring, both hydroxyl groups require alpha and beta agonist action, easily metabolized by COMT, catechol O-methyl transferase enzyme, decreases duration of action and oral activity, decreases CNS activity also. If there is no substitution on the benzene ring, there is no any activity, that is decreases in the activity. Substitution on the aromatic. Replacement of the catechol function of isoproterenol with the resorcinol structure gives a selective beta-2 agonist, that is beta-proterenol. It will longer the duration of action as because the resorcinol ring is not a substrate for the COMT enzyme, catechol O-methyl transferase. Substitution on the aromatic ring. Replacement of the meta-hydroxyl group of the catechol structure with the hydroxy-methyl group gives agents such as albuterol, selective beta-2 agonist. This is the structure. Removal of the para-hydroxyl group from E gives phenylephrine, which lacks of beta action but has less alpha 1 agonist property. Catecholamines without hydroxyl group. Loss of direct sympathomimetic activity becomes indirectly sympathomimetic. Not metabolized by COMT enzyme, and they are only active and have longer duration of action. Example amphetamine. This is the synthesis of phenylephrine. It is synthesized from 3-benzyloxybenzaldehyde when reacts with the ethyl bromoacetate to give ethyl 3-benzyloxyphenyl 3-hydroxypropanoate. This compound, again treated with nitrate, undergoes nitration to give an intermediate compound which gives oxazolidine later. This is the oxazolidine nucleus is formed. The compound is then reacted with sodium hydride in presence of methyl iodide. This is the sodium hydride and methyl iodide MEI to give 5,3-benzyloxyphenyl 3-methyloxazolidine to own, which on reduction gives phenylephrine. This is the final structure of the phenylephrine. These are some books as a reference I used for the preparation of this video.